In section 10.5, we are going to begin graphing rational functions. So the first thing that I want to do is give you the steps that you should follow to graph a rational function. First of all, you're going to find any intercept. Remember that an x-intercept is where the equation equals 0, where y equals 0. These are going to be fractions. Fractions are 0 when the numerator equals 0. So to find your x-intercepts, you're going to let the numerator equal 0. To find y-intercepts, you're going to put 0 in for x. Then you're going to find your vertical asymptotes. These occur where the denominator equals 0. Then you're going to find horizontal asymptotes. To find horizontal asymptotes, you compare the degree of the numerator and the denominator. The degree is the highest power of x that shows in each place. If the degree of the numerator is less than the degree of the denominator, then y equals 0 is automatically the horizontal asymptote. If the degree of the numerator equals the degree of the denominator, you put the leading coefficient over the leading coefficient, and y equals that number is your horizontal asymptote. If the degree of the numerator is larger than the degree of the denominator, there is no horizontal asymptote. Then you want to find any maxima or minima using the first or second derivative test. I generally use the first derivative test. Find any inflection points, which means you need the second derivative. And then find any extra points if you don't have enough information as yet. Before we start graphing an entire problem, I want to practice finding horizontal asymptotes. So when you have a problem like this of y equals 5 over x minus 7, the degree of the numerator is 0 because there is no x in the numerator. The degree in the denominator is 1 because the highest power of x is 1. So, because the degree of the numerator is less than the degree of the denominator, your horizontal asymptote is y equals 0. On this second example, we have y equaling 3x plus 7 over x minus 2. The numerator is degree 1 because we have an x to the first. The denominator is also a degree 1. When the degrees are equal, you find the leading coefficient. The leading coefficient means the coefficient of the highest power of x. The only power of x we have is x to the first, so the leading coefficients are 3 and 1. So your horizontal asymptote is y equals leading coefficient over leading coefficient, which is just 3. On this next example, the numerator is degree 1, and the denominator is degree 2. So, because the numerator is less than the denominator, your horizontal is automatically y equals 0. On this one, our numerator is degree 3, and our denominator is degree 1. Anytime the numerator is larger than the denominator in degree, there is no horizontal asymptote. Now we are ready to actually graph a rational function. The function we are going to look at is 1 over x plus 2. Let's look for our intercepts first. Remember, for the x-intercept, the whole fraction would have to equal 0, which means that the numerator would have to equal 0. In order for the numerator to be able to equal 0, there needs to be a variable in it. And this numerator has no variable. So what that tells me is that there is no x-intercept. For y-intercept, you put 0 in for x. If we did that, we would have 1 over 0 plus 2, which is 1/2. A y-intercept is a point, so we would write it as 0, 1/2. Vertical asymptotes are where the denominator equals 0. This denominator would be 0 at -2. A vertical asymptote is a line. You must write it as the equation of a line. So your vertical asymptote will be x equals -2. Horizontal asymptotes. Look at the degree. Numerator is degree 0, denominator is degree 1. So because the numerator is less than the denominator, it's automatically y equals 0. Now we need to find where it's increasing or decreasing. So we need the first derivative. To help us find the first derivative, I'm going to go back up to the original and rewrite it as x plus 2 to the -1 power. I'm going to pull that numerator up to the front. This will allow me to do the chain rule instead of the quotient rule to find my derivative, and that's going to be easier. So, f prime. Doing the chain rule, we're going to drop the 1 to the front. Inside will stay the same. New power, we go down by 1, so it's the -2 power, times derivative of the inside, which is 1. That can be rewritten as -1 over x plus 2 to the +2. So now we need to look for critical values. Critical values for a rational function are where the numerator equals 0 or where the denominator equals 0. Let's write a note for that. This numerator cannot equal 0 because there's no variable. The denominator equals 0 at -2. So our only critical value is x equals -2. We're going to put that on the number line. Now in this case, this is where the derivative is not defined. Most of the time when we've done this, we've put it equals 0 at those numbers. But in this case, it's where the derivative is not defined. We're going to test in f prime. Let's do -3. If I put -3 in that derivative, I will have -1 over -3 plus 2, which is squared. So I'm going to get a over a positive, which gives me an overall sign of negative. Now let's test 0. We would have negative 1 over 0 plus 2, which we are squaring. Numerator is still negative. Anything squared is positive. So we are also negative on the right side of negative 2. So as far as increasing and decreasing, we are increasing nowhere. We are decreasing from negative infinity to negative 2. We cannot just say negative infinity to infinity because this function does not exist at negative 2. So we have to break at that negative 2. So now we know that everywhere that this function exists, it is decreasing. The next thing we want to know about is concavity. So I'm going to move up screen. My first derivative, remember, was negative 1 over x plus 2 quantity squared, or negative 1 times x plus 2 to the negative 2. The reason I need that is because I need my second derivative. For my second derivative, do the chain rule on this version. Drop the negative 2 times the negative 1. You now have positive 2. Inside stays the same. New power, we go down by 1 to negative 3 times derivative of the inside is 1. So that becomes 2 over x plus 2 to the positive 3. Just like on the first derivative, your possible inflection points are where the numerator equals 0 or denominator equals 0. Just like previously, this numerator cannot equal 0. There's no variable. But the denominator equals 0, which means that the second derivative does not exist at x equals negative 2 again. So we are still going to use negative 2 on our number line. And this is where the second derivative is not defined. We're going to test in the second derivative. Let's do negative 3 again. We would have 2 over negative 3 plus 2 to the third. Well, the 2 is positive. In the denominator, negative 3 plus 2 is negative 1 to the third power is going to be negative. So the left side of 2 is negative. Let's test 0. That would give us 2 over 0 plus 2 to the third. Our numerator is positive. Our denominator is positive 2 cubed, which is also positive. So the right side of negative 2 is positive. What we know now is that we are concave up from negative 2 to infinity. We are concave down negative infinity to negative 2. Negative 2 is not an inflection point. Because f double prime does not exist at negative 2. On this screen, I have summarized all the information that we found in the work up above. We're going to put these things into place on our graph. We don't have any x-intercept, but we have a y-intercept at 0, 1/2. We have a vertical asymptote at x equals negative 2. And we have a horizontal asymptote at y equals 0. So our axis is also an asymptote. Let's find some extra points. Because all we've got right now is that one single point, and it doesn't give us any information about the shape of the graph. What I do to find extra points is look on each side of the vertical asymptote. And plug in a couple x values on each side of that. So I'm going to take negative 3 and plug it into the original equation. If you do that, you get negative 1. Put negative 1 into the original equation. You get positive 1. If you put negative 4 into the original, you get negative 1/2. And if you put positive 1 into the original, you get 1/3. So putting those into place on our graph, at negative 3, we're at negative 1. Negative 1, we're at positive 1. Negative 4, we're at negative 1/2. At positive 1, we're at 1/3. So what I see now is that this is kind of a curved shape, and they have to stay within the asymptotes. So on the left side of the vertical asymptote, we've got this kind of a shape. And on the right side of the vertical asymptote, we've got that shape. Notice how the function is always decreasing on both pieces, like we said it should, and that it is concave up from negative 2 to infinity, and it is concave down from negative infinity to negative 2. So it does match the characteristics that we came up with. The second example that we are going to do is f of x equals x plus 1 over 2x minus 1. Always find your intercepts first. The x-intercepts are where the top equals 0. This numerator would equal 0 at negative 1. So your x-intercept is the point negative 1, 0. For your y-intercept, put 0 in for x. If you put 0 in where the x's are, you will get the answer of negative 1. Horizontal asymptotes, compare the degrees. The degrees are the same. They both have an x to the first. So if we put leading coefficient over leading coefficient, our horizontal asymptote will be y equals 1/2. Vertical asymptote is where the denominator equals 0. And if you set 2x minus 1 equal to 0 and solve, you will get 1/2. So x equals 1/2 is your vertical asymptote. Next, we need to find out about increasing or decreasing, which means we need the first derivative. So looking at our original function, Because there is a variable in both the numerator and the denominator, you must do the quotient rule to find this derivative. So the quotient rule says start with the low as is times derivative of the high is 1 minus the high as is times derivative of the low, which is 2, all that over the low squared. 2x minus 1 times 1 gives us 2x minus 1. Distributing the 2 and the negative, we will get negative 2x minus 2 over the quantity of 2x minus 1 squared. Well, 2x minus 2x is 0, so our derivative is negative 3 over 2x minus 1 quantity squared. Your critical values are where the numerator equals 0, but this numerator has no variable, so it can't equal 0. Or where the denominator equals 0. This denominator equals 0 at 1/2, so your critical value is x equals 1/2. Set up a number line with 1/2. This is where it is, the first derivative is not defined. And then we're going to test in the first derivative. Let's do 0 for the left side of 1/2. We would have negative 3 over 0 minus 1 being squared. We would have a negative over, anything squared is positive, so the left side is negative. If we test 1 in our derivative, we will have negative 3 over 2 minus 1 that we are squaring, which is still going to be a negative over a positive because of that squared in the denominator. So what we know then is that it is increasing nowhere. We are decreasing from negative infinity to 1/2, and then again from 1/2 to infinity. Remember, we can't just say negative infinity to infinity because neither the function nor the derivative are defined at the value of 1/2. I rewrote the first derivative because the next thing that we need to do is find the second derivative for concavity. When you have a function where you have a constant over a quantity, you can always rewrite that as the constant times the quantity to the negative power. The reason that we like to do this is because finding the derivative in this format is faster. It's the chain rule instead of doing the quotient rule. So now the second derivative. We drop the power times the coefficient, which will give us positive 6, times the inside stays the same, go down by 1 to negative 3, times derivative of the inside is 2. This gives us 12 times the quantity to the negative power, or 12 over the quantity to the positive power. Now that we know our second derivative, we need to find the possible inflection points. The possible inflection points happen where the numerator equals 0 and where the denominator equals 0. this numerator cannot equal 0 because there's no variable. The denominator equals 0 at x equals 1/2 again. So we're going to put 1/2 on our number line. And this is where the second derivative is not defined. So now we're going to test in the second derivative, and let's do 0. If we put 0 into that second derivative, we will have 12 over 0 minus 1, which we are cubing. Well, the numerator's positive. The denominator, you're going to have -1 to the third power, which will be negative. So the items to the left of 1/2 are going to be negative. If we try 1, we will have 12 over 2 minus 1 to the third. The 12 is positive. 2 minus 1 is 1 to the third, which is positive. So the items to the right of 1/2 are positive. We now know that we are concave up from 1/2 to infinity, and we are concave down from -infinity to 1/2. We have no inflection point because that 1/2 was where the second derivative did not exist. So it cannot be an inflection point. I have summarized all of our information again so that we can sketch our graph. We have an x-intercept at -1, 0, a y-intercept at 0, -1. We have a horizontal asymptote at y equals 1/2. And we have a vertical asymptote at x equals 1/2. In looking at this, notice that the 2 points that we know are both on the same side of the vertical asymptote. So for extra points, I'm going to find one more on the other side, on the left side of the vertical asymptote. I'm going to put in -2. If I put -2 into the original function, I get 1/5. Now I'm going to find some points on the right side of the vertical asymptote. So I'm going to put in 1, and if I put 1 in the original, I get 2. Put 2 into the original, you get 1. Put 3 into the original, you get 4/5. Now plotting those points at -2, we are at 1/5, so we're just over the 0. And if you look at this, you can see how we're following the shape of the asymptotes, and we are decreasing, which we said we should be, and we are concave down, which we said we should be. On the right side of the vertical asymptote, we have a point at 1, 2. We have a point at 2, 1. And we have a point at 3, 4/5. So it's almost at 1. So again, as you can see, we are fitting within the asymptotes. We are decreasing. And this piece is concave up, like we said that we should be.